turning effect of a current carrying coil in a magnetic field. This is a magnet. Again, there are two magnets. This one is a north pole and this is a south pole. So between these two magnets, there is magnetic field. This magnetic field flows from the north pole to the south pole. Okay, and then there's a current carrying coil. Okay, so current carrying coil means that this coil is connected to this electric source. Okay, electric source, maybe it's a batteries or the dynamos. So there's a current flow into the coil. Okay, go into the coil and then flow out, go into the coil and come out. So what will happen to this coil when there's a current flow in and out? Now we learned that when there is current flow into a magnetic field, a force will be produced, right? A force will be produced, and the directions of the force can be determined by Fleming's left-hand rules. Now if we use Fleming's left-hand rules for this one, okay, when the currents move into the coil, let's see what's the directions of the force. First we use our left hand, and then so this is the index finger. Okay, the index finger shows the directions of the field. The directions of the field. Okay. So that's the first thing. Second, the currents move inside, right? The current move inside. So this is the directions of the currents. And then the thumb. Okay, the thumb will point upwards. If this is your hand, right? This is your thumb. So if you use your left hand, use Fleming's left hand rule. So the field is from north to south, and then the current move in. Okay, the current move in. So the thumb point upward. The thumb point upwards. So it means that the force, there's a force that push this wire upwards. Okay, so when the current flow here and then come out, and the directions of the current change, if you use Fleming's left-hand rules, you will find that the force, okay, the force will act downwards. So at the left-hand side, the force move upward, and at the right-hand side, the force move downwards. These pairs of forces, there are two forces, right? So this pair of forces, it will produce we call this a torque or a couple. A torque or a couples. So these two forces will produce a torque or couples that make this coil rotate. So when this one go up, this one go down. And this part is fixed. It's fixed at this something here. Okay. So this will make this coil rotate. Okay, it will make the coil rotate. Make the coil rotate. So in this case, it will rotate clockwise. It will rotate clockwise. So we say, if there is a current carrying coil placed inside a magnetic field, this current carrying coil placed inside a magnetic field, it will produce a turning effect of a current carrying coil in a magnetic field. So, and this turning effect will make this coil rotate. So if a current carrying coil is placed in the magnetic field, a pair of forces will be produced. One go up, one go down. So two forces. This is due to the interactions of the magnetic field and of the permanent magnet and the magnetic field of the current carrying coil. So there are two magnetic fields here. One is from the permanent magnet. Another one is from the current that flow into the coil. So these two magnetic fields interact and produce a catapult field, and produces two forces that rotate this coil. So that's what happens if we put a current carrying coil inside a magnetic field. So this turning effect is due to the interactions of the magnetic field of the permanent magnet and the magnetic field of the current carrying coil. For example, this is the permanent magnet north to south. And this is the current in the coil. There's a circle with a dot and a circle with a cross. Circle with a dot means that the current come out. The current come out. So this one, the current come out. This circle with a cross means that the currents go inside. And the red one is the magnetic field produced by the current. When there's a current flow in the conductors, then it will produce a magnetic field. So this is the magnetic field produced by the current. This one is also the magnetic field produced by the current. Now, these two magnetic fields, the red one and the black one, will interact. And as what we discussed last week, if the directions of the field is the same, it will make the field become stronger. So this part, the two field move in the same direction. The red one, it move here and then move to the right, right? So the field of the permanent magnet also move to the right. So here, same directions. So let me label here. So here, the field move to the right. And the field of the permanent magnet also to the right. So at this place, the field has same directions. Same direction. So it will move the field become stronger. So it will produce a stronger field here. And this place is in the opposite direction. So therefore, the field is a weaker field here. And here, same directions, stronger field. Here, opposite direction, so weaker field. Weaker field. As a result, the interactions of these two magnetic fields will produce something like this. So from here we can see that this is a stronger field, and this is a stronger field here, and this is a weaker field here, and this is a weaker field here. So this is a catapult field. And we also learned that for the catapult field, it will generate a force. Generate a force that moves the conductor from the stronger field to the weaker field, right? So it produces two forces, from the stronger field to the weaker field, from the stronger field to the weaker field. So this is stronger, weaker field, stronger, weaker field. So two forces is produced from this to push the conductors from the stronger to the weaker field, from the stronger to the weaker field. So these two forces will make the coil rotate. Okay, it will make the coil rotate. You need to know how to draw this. Sometimes in the exam they may ask you to draw this. After the interactions, so the patterns of the field. The patterns of the field. So make sure that you know how to draw this. Let me show you. Okay, let me give you the guides on how to draw this field. Okay, let's say this is north and this is south, and this is let's say this is a cross. Okay, this is a cross. And this is a dot. Now, if this is a cross, then it will produce a stronger field here, weaker field here, and a stronger field here, weaker field here. Okay, because the directions of the current is opposite of this one. Okay, this one come out, then the stronger field here. But this one it go inside, the stronger field is here. Okay, so after you know where is the stronger field and where is the weaker field, so then we start drawing. So we start from see here, this is the center. So we start slightly below the center. If you draw this, okay, you see this line is very close to the wire, okay, and this one is also very close to the wire. If you draw this, then you're going to have a problem here, because after this you have no space for you to draw the second line here. So when you draw this line, be very careful. Okay, first, the field line is very close to the first wire, but it's far away from the second wire. I'll show you later. So this one, let's erase first. Okay, let's erase first, and then this one, try to draw it a little bit far away from that, so that when you draw the second lines, okay, when you draw the second lines, you have space for your second line. Okay, see. So can you see that? So because the second line also, I need to draw it here. So after that, you can draw the weaker field here. Okay, so this is a weaker field, and this is a weaker field. So that is how we draw this catapult field. Catapult field that caused by this current carrying coil. Faisal asks, a magnetic field cannot intercept. Yes, cannot intercept. Okay, it cannot cross each other's. You cannot draw another one like this. Cannot, because magnetic field cannot intercept. So that is how we draw the catapult field. So the directions of the force can be determined by Fleming's left hand rule, because sometimes they may ask you to find the directions of the rotations, whether it's clockwise or anti-clockwise. So you can use a Fleming's left hand rule to find the directions of the force, as I show you just now. Since the current in both sides of the coil flow in opposite directions, so the forces are in opposite directions. So the two forces in opposite directions constitute a couple, which produces a turning effect to make the coil rotate. So one force go up, one force go down. This will produce what we call a couple. Okay, a couple, or sometimes we call this a torque. A couple or the torque. And this couple will make this coil rotate and produce a turning effect.